let's now calculate the capacitance of our parallel plate capacitor. So this is our first example. And suppose we have a plate, another conducting plate, and we put a charge minus Q on this one and a plus Q on this one. The plates are separated by a distance d, and the plates have an area, I'll call it A plate to distinguish that. Now, what we know is that the charges on the positive plate will appear on the lower surface, and that will give a plus sigma. And the charges on the negative plate will appear on the surface between the plates, minus sigma. And this is an example, the simplest example, of a parallel plate capacitor. Now, what we'll do is we'll have very long plates. So these are, quote, infinite plates. And the reason for that is we can neglect edge effects. For a real capacitor, it's a little more complicated, a parallel plate capacitor. But for the moment, we can neglect edge effects. And we can calculate the electric field between the plates then by using Gauss's law. Now, this is where Gauss's law is tricky, which we've already done for the parallel plates. But let's just look at that upper plate for a moment, just to remind you of how a calculation goes. Let's blow it up. And what we have here is that the charges are down here. This is our plus sigma. This is the conductor of the upper plate, where E is 0. And so I can choose a Gaussian surface where I put one end in the plate, the other end between the plate, just so that our diagram looks like this is our lower plate. Now, Gauss's law, the field in between the plates is due to both plates, minus sigma and plus sigma. Gauss's law is dealing with the total field that's already the superposition of these two fields. Because E is 0 on the top, we know that by Gauss's law, and we've done this calculation before, but it can't hurt just to say it again. For this example, we have the total field due to both plates. It's only on one surface. The only flux is on this lower surface because this is the physical property of conductors. The E field is 0 inside the conductor. And over here, the charge enclosed, well, we see that there's a surface charge density. I'll shade it in. And this is not the area of the plate. This is the area of the Gaussian surface. And that's equal to sigma times the area of the Gaussian surface divided by epsilon naught. And so we see the E field is given in magnitude by that. Now, I'm just going to choose a coordinate system, y equals 0, y equals d, positive j hat is up. And so as a vector field, this is in the negative j hat direction. And so that's the electric field for the capacitor. We've done this calculation before. But when you want to now calculate the capacitance, it's Q over the absolute value of the potential difference. And in this problem, we know that the electric field is uniform. And we've calculated this potential difference before, but we don't really have to worry about it here because it's just the magnitude of E times the distance of d. Now, be careful because for other capacitors, E will not be uniform, and you can't make this simple calculation of the potential difference. This is just E times d. This is only for the parallel plate. Let's just make that absolutely clear. So now we've calculated E, and we have in magnitude sigma over epsilon naught times d. And the sigma that appears on these plates is equal to, let's just write it up here, sigma is equal to the total charge in the plate divided by the area of the plate. And so we get Q times the total charge on the plate divided by the area of the plate times epsilon naught d. And we get a formula for just the parallel plate capacitor. It's the area of the plate, epsilon naught over d, and that is our capacitance. Now notice, and this is true for all of our calculations with capacitance, that it doesn't depend on the charge on the plate. This is just a geometric property of our parallel plate capacitors. Proportional to the area, makes sense, the bigger the area, the more charge. Constant epsilon naught divided by the distance between the plates. And that's our first simple calculation. Remember, this is just the parallel plate capacitor. It's not a general statement about capacitance.